As lanthanide contraction, we can observe actinide contraction also. Lanthanides, the 14 elements, right from cerium to lutetium, they belong to 6th period. Likewise, in 7th period, we have right from thorium to lawrencium, 14 elements, so called actinides. Due to more effective nuclear charge, the electrons present in 5f orbital, they show poor shielding effect. As they show poor shielding effect, 5f electrons are effectively attracted by more than the nucleus of lanthanides. Hence, more decrease in size in the period is observed in actinides due to more effective nuclear charge than lanthanides. Hence, actinide contraction is more than lanthanide contraction. Atomic radius. The distance between the nucleus and the outermost orbit is called atomic radius. It is measured by X-ray diffraction, electron diffraction, IR infrared spectroscopy, NMR nuclear magnetic resonance spectroscopy. And this atomic radius, it is expressed in several ways. Covalent radius, metallic radius or crystal radius, and van der Waals radius. Covalent radius, it is defined for the two bonded atoms of the same nonmetal. For example, H bond H, F bond F, Cl bond Cl, so on. Here, by definition, covalent radius, see this H atom, imagine this H atom, they are bonded together. After formation of the bond, the distance between the nucleus of hydrogen atom and another nucleus of hydrogen atom, this distance is so called diameter. This diameter by 2 is called covalent radius. By definition, the half of the distance between the two centers of the two nuclei of the two covalently bonded similar atoms, same atoms present in the molecule. Mathematically, covalent radius equals to half of internuclear distance between the two covalently bonded similar atoms H and H by 2, that is diameter by 2, that is called covalent radius, defined for H bond H, F bond F, Cl bond Cl. Crystal radius, otherwise called metallic radius, it is defined for two adjacent metal atoms present in the crystal lattice. Actually, so one metal atom approaching the other metal atom, the total that much closeness. So, once they are approached so closely, the distance between the two centers of the two nuclei of the two metal atoms present in crystal lattice is called crystal radius, defined for metal atoms. Van der Waals radius, it is defined for molecules. Imagine this is H bond H, H2 molecule, this is H bond H, H2 molecule, and here van der Waals radius, it is defined as half of the distance between the two successive nuclei, two successive nuclei of two atoms present in two adjacent molecules which are approached together. It is defined for non-metals. Actually, van der Waals radius, it is for two molecules which are coming to the closed vicinity. No bond is involved between this molecule and this molecule. Hence, van der Waals radius compared to metallic radius, compared to covalent radius, it is maximum. In general, van der Waals radius is maximum and covalent radius is minimum and it is medium. Maximum, minimum and it is medium. ionic radius. It is defined as the distance between the nucleus and the outermost orbit of the ion is called ionic radius. Direct calculation of ionic radius is not possible since we cannot find independent cation or independent anion because they are held by strong Coulombic electrostatic force of attraction, no free ions. Hence, direct calculation of ionic radius is not possible. Hence, ionic radius is defined for ionic crystal. So, it is actually effective distance from the nucleus of the ion and its valency shell, outermost shell, present in the crystal, ionic crystal. And here to calculate ionic radius, it is what we calculate is inter-ionic distance between the two oppositely charged ions, inter-ionic distance. Cationic size. For example, sodium atom, atom number 11, it has 11 protons and 11 electrons. Electronic configuration 1s2, 2s2, 2p6, 3s1. So, first orbit 1s2, 2s2, 2p6 and 3s1. After losing one electron, it becomes Na plus. It has 11 protons in the nucleus but only 10 electrons. That is 1s2, 2s2, 2p6. That is what we have first orbit and second orbit. Here, as we have more number of protons than electrons, more protons in the nucleus, more nuclear charge, more attraction by the nucleus. More attraction by the nucleus, electrons they come closer. Once they are coming closer, ionic size decreases. In general, cation size is less than its atomic size. Similarly, in case of Mg atom, 12 protons, 12 electrons. But after losing 2 electrons, it is now 12 protons, only 10 electrons. More number of protons, more nuclear charge, electrons are coming closer, hence size is less than its atomic size. Same is the case with Al plus 3, its 13 protons, 10 electron size is less. And compared to Al plus 3, Mg plus 2 and Na plus, so-called isoelectronic species, as in Al plus 3 compared to Mg plus 2, Na plus, as we have more protons, more number of protons in the nucleus, more attraction, less size. Hence, Al plus 3 size is less than Mg plus 2, less than Na plus. Anionic size. For example, chlorine atom. It has 17 protons, 17 electrons. It is neutral atom. So, here by accepting one electron, it becomes 17 protons, 18 electrons. That is stable noble gas configuration are gone. Now, it is called chloride ion. In this anion, compared to protons, we have more number of electrons present in the orbits. In the orbits, among the electrons, more repulsion, more size. In general, anionic size is greater than its atomic size, since anion contains more electrons. Among electrons, more repulsion results in more size. Similarly, oxide ion, 8 protons but 10 electrons, more repulsion among the electrons results in more size, hence oxide ion size is greater than oxygen. In case of isoelectronic species, that is C-4 ion, carbide, nitride, oxide, fluoride. In case of carbide, only 6 protons but more number of electrons. More number of electrons, more repulsion among the electrons, more repulsion among the electrons, more size. Hence, C minus 4 size is more than N minus 3, than O minus 2, than F minus 1, since it has more protons. Hence, size is less. When compared with iodide ion, iodine atom and iodine cation, in case of iodide ion, we have all the things 53 protons, same atomic number. But iodide ion, more electrons, more repulsion, more size. And I plus ion, less number of electrons, more protons, more attraction. More attraction, less size. Hence, minimum size. More electrons, maximum size. And atom, medium size.